as I try to unmute myself. All right, here we go. So it is 3 p.m. Let us get going. First things first, people have not been signing the STCW form. All right. This needs to be done by Friday at the latest. Don't make me chase you. If I have to chase you, bad things happen. Not to me.
Does that include the lab sheet?
Yep, I'll go over that in a second. But yes. So the STCW, I'm not going to name everybody, but I will name the people who did it. So Eric with a K, Anthony, Brandon, yes, Ryan Charles, Zoboy, ZYBO. I'm not pronouncing that right. Is the
Zybo.
R there? What is it?
Zybo.
Zybo. Okay. If I get it wrong, guys, correct me. Brian, Ethan, Mathis, and let's see. I think there was a couple more. David and Maxim. You were the only people who have done it. Everyone else, you be better. All right. So going from there. All right, let's go into what I have for you today.
Oh, excuse me.
Yes.
I'm sorry. I forgot where that form is.
I will show that again. Don't worry.
Professor, I emailed it to you also yesterday.
Okay. Make sure you submit it. That's the only way I'm going to be accepting it. All right.
Oh, I
Otherwise,
have to submit it? I thought it was okay. No
Yep.
problem.
So, all right. Otherwise, I would get like 250 some odd emails, considering this is a second form you're going to have to sign. This one I wrote up. All right. So it has basically, it's just acknowledging that you guys understand what's going to happen. All right. I state your name, write your name here, sign, date. I couldn't make this one signable. I didn't feel like paying for Adobe again. But what you can do is if you come up here and you still click the sign document. All right. And again, if you want to print this out, you can print it out. All right. You can also click here and you can add, you can add your name. All right. And then you go to signature and you could put the signature where it needs to go and all that kind of other stuff. All right. So going from there, basically, these are two events that could happen. One, we never come back to school this semester. All right. Catastrophic failure, basically, we don't return to school. All right. If that happens, you will have to take 540 lab at the next semester it's offered, whether that be the spring or the fall of next year. All right. If that happens, we can't do the steam tracing or the steam plate. All right. So that 10% will be broken up into the basically 2% each one. So quizzes will go from 15, 17. All the tests will get 17% each. And then the final will be the 32. All right. Same thing will happen if we return to in person and then we get shut down by the state because we have too many COVID cases. All right. So same thing again. This is a 14-week lab that we push down into 13-week semester, which is getting pushed down into, again, basically 11 weeks. All right. So if you don't attend all of them, then you're not going to be able to go to get on cruise. All right. So this is a mandatory piece. All right. So sign, date this, get it to me by Friday. All right.
So if we print that out, sign it,
That's
we could
totally fine
still
too.
submit it.
Yep. Scan
All
it
right,
in,
thank you.
sign it. I just made it so that way if people don't have scanners, which is more than you would think. When I went to school back in 2011 as a freshman, every single time you bought a computer, the big deal was like, oh, you get a free printer and scanner. Now you guys get like headphones, right? Or something, whatever it comes from.
That one under the lab section of Blackboard, or is that in the lecture section of Blackboard?
All right, good point. There will never be a time I will use the lab section of Blackboard. All right, so let me share this screen. There we are. All right, so this is what you see when you come in, go into modules. All right, important information. And on important information, you can download them right here. All right, or if you click them, you can still download it right here. And then I need you to attach the file using that piece of information. All right. They're not worth any points, but if I start chasing you, they might become points, and not in a good way. All right. All right, let's see. Everybody is aware that there's my YouTube channel. All right, so that way if you miss anything on lecture, or if you have bad internet and you have to only come in via voice and you have to see it later, this is the ability every single time. I'm not sharing the screen. Every single time at the end of the day, I upload it. All right, it's just pure upload. There's no editing or anything like that. So you go into playlist, you can see that there's the 3 p.m. lecture for the year 21. There's the 10 a.m., 11:30 lecture. All right, so you can watch this class, or if you want to see maybe another class, if they have other questions, you can always do that as well. All right. Anything about that before we start for the day? All good? All right. Let me set up the slideshow and we'll go from there. Shoot, that's not what I want to do.
I think you and my brother are in the same section.
Oh, Cucciaro.
Yep.
Yep. That we were. How's he doing?
He's doing well. He's like
Yeah.
home now. He was out at sea for a year.
Jesus. Did he do MSc?
Yep. Artie, you want to come say hi?
Sure.
Why am I frozen?
Hey, what's going on?
Hey.
I can't hear.
Yeah. He said hey.
Hey.
Am I muted or something right now? Or what's going on with that? Let's see.
You're just frozen.
I'm just still frozen. Give me a second.
You're good now.
Now I'm good. All right, let's try this again. That was super weird. Am I still good?
Yeah, it's just a blank slide now. It's just values, system, nomenclature.
All right, sweet. Okay. Let's go. Oh, and you guys saw that I posted the slides to the PowerPoint, right? That got posted on Monday afternoon. All right, good. All right. Just as a quick reminder, our isolation valves of what we were looking at, we are going to basically moving on from there. All right. If it wasn't for valves, all right, if everything was a perfect world and, you know, pumps didn't break or fuel oil heaters didn't cool down or anything along those cool down, if fuel heaters didn't get clogged up, there would be no reason to have any sort of isolation valves. All right. We need isolation valves so that way we can work on equipment. We can redirect flow. All right. That is why we have them. All right. Now, moving forward to control valves. These are going to be, one type is constant pressure regulator. All right. So this is the diagram. This is the symbol for one of those. All right. You can also see something that will look like this. This is what you'll see more often than not on a tracing. All right. But in lecture, this is what the symbol is going to be used. All right. They mean one and the same. going through that, we can see that we have this dotted line that comes up, goes over, and then terminates right down here. All right. That termination, that spot means that at that singular point right there is where we are sensing. All right. So that is our sensing point. This is where we are controlling it. And again, we have inlet and outlet. So that way, if this equipment breaks, we can replace it, fix it, all that other stuff. There's our isolation valves. All right. So we have a regulating valve, a pressure regulating. All right. This one is maintaining downstream pressure. So if we look at it, the way we always talk about, the new word that we're learning basically with this is downstream and upstream. What do they mean? What do they are in reference to? All right. And the best way to think about it is if you are standing on the edge of a stream. All right. We'll do position 1 and position 2. And then we got letters A, B, C, D, and E. All right. If you're standing at position 1, that's where you are in location. And the river flows this way. What is upstream to you?
A.
So A is upstream, right? Because that is the farther up of the stream. The stream is flowing that direction. And then what would be considered downstream in position 1?
E.
Well, B would be pretty much even with you.
I said E.
Oh, E, yes. But so would C, D, and E, right? So if we start walking with the stream and we go and we wander down to position 2, what does C become? It was downstream at position 1. Now what is it? It's upstream, correct. All right. So change U for a valve. All right. You are no longer you are a valve. So over here for this valve is going to be considered upstream. At position 2 is considered downstream. All right. It's all in relationship to this valve. Okay. Make sense? And as you change your position or you change equipment, position 2 may be a pump. All right. Well, as you change position or change equipment, your downstream, upstream terminology will change. All right. It's in whatever you're referencing to. So this one is maintaining downstream pressure. We know that by a couple of things as we can start to decipher these types of valves. All right. We have a spring. We have a upward seating valve. All right. And we have this black material right here. That black material, you can kind of think of it as a gasket. Oop, I dropped my pen. As a gasket. All right. It's super thin, super strong. It's usually made of metal. All right. Sometimes it will be made of metal and a rubber. It all depends on what type you have. All right. And what's happening is that it's going to bend. It's going to manipulate up or down. All right. I'm going to draw this a little bit bigger so that way we can kind of see what's going on down in that area. All right. So that black line is going to be this bottom bowl part. All right. This blue is going to be that gasket material. All right. There's our line that's right here. Okay. And then I'm going to draw in red the stem that goes down into the valve. All right. Along with, oh, come on. Don't give away the answers. Along with the valve. All right. Last but not least, we have our spring. All right. Does that make sense to everybody that they're seeing? Okay, good. So we are sitting here and we have three things that we have to pay attention to, and that will be able and allow us to decipher any one of these valves of what's happening. All right. The first thing is the spring. And it comes down to, where is the spring? Is it above? Is it below? Where is it acting on? Where is the force going to be applied to? All right. All of those questions go to that. Then number two is, where are we taking a sensing from? Where are we concentrating? Where is our input going into the system? All right. Is it coming in below? Is it coming in above? Are we taking it from the upstream side, or are we taking, in this instance, the downstream side? All right. So where's the sensing line? And then finally, number three, is it a upwards or downwards facing valve? Is it going to seat in the upward direction, or is it going to seat in the downwards? All right. So the physical valve itself. Okay. Those three things, you'll be able to understand all of these valves. So first things first, we're going to be doing with this with pressure, because we're doing pressure regulating. If I say right here is 60 PSI, okay, and this is just a bigger version of what's happening here. Is 60 PSI the same over here and over here and in here, or is it different?
It's different
Why would it be different?
because it, like, as it's flooding in, it's like going to be moving faster. If it's further down the pipe, then it won't be as as fast.
So you're saying there, so way down the pipe, there's going to be line loss. Yes. But in this instance, we're talking about a mere couple of inches. Okay. So if we are sitting here and we have 60 PSI sitting here, we are going to have 60 PSI on every single surface in here. Remember what PSI stands for. All right. It's pounds per square inch. So every square inch we have, 60 pounds of force is being applied to it. All right. So that means if we have 60 PSI here, we have 60 PSI in here, because we have probably about a 1 inch sensing line. All right. So we have 60 pounds force going up, 60 PSI going upwards. All right. Now, erase some of these arrows. Now that we know that, and like I said, this is just a random number we applied. Let's apply another random number, above or below, it doesn't matter, for a spring, because the spring is going to be what is our control. All right. We can control the spring tension via this nut, via this bolt. So do we want to go above or below our number? What do we want?
Below.
All right. So our spring is going to have 40 pounds force. All right. So this spring is able to push down 40 pounds. All right. 40 PSI of force. Is it 40 or 60 a larger number?
60.
60.
60. So what will happen?
So
Pressure's
water
going to push up
travel.
against the spring.
It's going to push up against the spring and it will overcome that spring force, correct?
Yeah.
So since the valve stem is attached to that blue line, that blue baffle, that blue gasket, what will happen to the valve?
It'll open.
Shut itself off.
It will shut itself. All right, because the valve will travel upwards, because 60 is larger than 40. It will overcome the spring force and it will travel upwards, and it will close because it's upward seating. All right. Everybody see that these things are on an angle, right? And it will seat in an upward face. correct? All right. That's why the valve is the third portion and the important part. Because if the valve was flipped upside down, just this part right here, right? That was flipped upside down, it would be a totally different effect. It would open the valve rather than close it. And now we can check and make sure we're correct. All right? Because if we have 60 pounds force coming in and we have a set point of 40, that spring wants to be 40. All right? And we have 60 pounds on the downstream side. Well, we want to maintain only 40. So that valve will close, and whatever equipment is down the line will use up that pressure, will use up that fluid, whatever we are using, say water. Now, that 60 goes to 59, to 50, to 45. Once it reaches 40, that valve has been closed that entire time. So as soon as it reaches 40 and then goes down to 39, what happens?
It opens
System
back
will
up.
open back up.
It'll open back up because it won't be able to overcome that spring pressure. And now we'll add a little bit of fluid in, right? Remember, we're taking just a straight snapshot of what's happening here. 39, 40, everything like that. 60, all of those numbers, we're just doing a very extreme snapshot. These things aren't going to be wide open or closed. These are throttling valves. They're control. Okay? So at 39, it's going to be slightly open. But at 60, that thing's going to be slammed shut. Same thing as if we had 20 PSI down here, half of what we needed. That thing's going to be pretty much open, right? But compared to like 39 or 38, it's going to be slightly open because we only want a small amount to come through. We want to get that 40 PSI. We don't want that thing to just hammer in full force. Correct? We may have over here, in reality, 600 PSI. And we want only 150 over here. All right? That's the things that we have to think about. And that's why I was saying that you could just choose whatever random numbers you want. Flipping them around won't matter. And I'll show that. Get rid of these numbers here. If we sit here and we get rid of that 40 and that 60, get rid of that arrow and that arrow. That was 40 up there, right? So let's flip it. That's going to be set at 60. Down here, set at 40. What happens?
System opens up.
The valve will open up because we want more pressure, right? So we want 60. So we're good. And if we take this and we say this is 70, that's larger than 60, and that will close the valve, right? So we will maintain what we want. We are maintaining the downstream side of the pressure. Does that make sense to everybody? Okay, good. So the regulating pressure is going to be the closing force, like we already discovered. All right. And the spring is going to be that opening force. Now we have a different valve over here. Same three principles apply. We have the spring, we have where is it sensing, and we have the valve. Is it upward or downward seating? Granted, these both examples have only an upward seating valve. But in the next slide, you will see a downward seating. All right. And you can have a sensing line that will come in on the bottom in this same way. All right. So don't think that these things are always going to lead to the exact same result. These are just the most basic and also the most simple, efficient way of doing these things. All right. So looking straight at this, what is the spring? Is the spring the opening or the closing force?
Your spring's the
Closing?
closing force.
Spring's going to be the closing force, right? Not just because it's below the baffle. All right. It's because this is going to close it with that force. It's where it's physically attached to. It's attached up here. Right? So if we had a spring that was worth at, let's say, 70 psi, we want to maintain our upstream pressure. So let's say we want to maintain 70 psi in the upstream. Well, if this is 40, what will happen? That means we have 40 up here as well, right? So 40 pounds being pushed down can't overcome 70. And now that valve will close and it will allow the buildup of pressure. All right? Because all we care about, and all this valve cares about, it doesn't know anything else in the world. All right? All it knows is what the pressure is on this piece of pipe at that moment and what is it going to do about it. It doesn't care if the engine room's on fire. All it cares is about this valve at what pressure is that system. All right? So the regulating pressure is going to be the opening force, and the spring is the closing force. All right? Any questions before we push forward? All right. So that's our control valve. Then we have a fuel oil pressure regulating valve. All right. Think about it. If we're using fuel oil, and the fuel oil we use on the ship is pretty much one step below, actually, sorry, it's one step above asphalt. All right. So that's some nasty stuff. We're lucky if these valves have like a half of an inch in between. An inch if you're lucky. All right. That fuel will clog that up so quickly and these things would just be trash. All right. So an analog version of what we use with this is using some sort of control air. All right. Some sort of air signal that will interact with those baffles, interacts with that sheet of very thin metal instead of the fuel. All right. Nowadays, you'll probably have a digital version where it will be a solenoid valve that will be motorized and it will open and close and it will be all electronic. But this is the analog version of it. It's very mechanical. All right. And you can see right here, as I said earlier, this one is an upward seating. Sorry, this is downward seating. And then this one seats in the upwards direction. All right. Sorry, that's downwards. This one's upwards. All right. So it seats, it's going down. All right. And you can see that crevice. These aren't the largest valves in the world. All the way up in this area up here, you can see that, basically that little hole right there. That little line, compared to that valve, that's the air line that comes in. So if we had fuel going in there, this would be a huge problem. All right. So going in on top, those are called direct acting, and below is indirect acting. All right. And that's just where the sensing line, that's where the line goes in. The other place we use it is the fuel oil temperature regulating valve. Again, like we talked about this, we go to pressure because pressure is easy. All right. So, but I said earlier, we could use sensors. Anything that you could measure, we can automate. All right. So this is a temperature sensor. All right. It goes in, it sends a signal to what's called a pilot valve. That pilot valve sends an air signal to another regulating valve. So it's going to be sending steam to our fuel heater based on the temperature of that fuel coming out. If we need more steam because the fuel heater is cold and the fuel coming out is cold, or we need less steam because it's at temperature already, or it's too hot a fuel. All right. Now, looking at it, these are our air regulated valves. This is our control pilot valve. All right. So we have high pressure steam going this way, and we have reduced pressure steam coming out of it. So this is an actual spot that we would have on the ship. So we would have 600-pound steam going in, and we would have what's called a reducing station and 150 psi steam coming out. All right. We do this because we want this to be like an auxiliary steam. You know, for any sort of heating, we don't need 600-pound steam going into a fuel oil heater. We would have massive heavy fuel heaters. That's just inefficient. We need 150-pound hot enough to warm up what we're doing. All right. We need 150-pound steam for heating up any of the hot water on the ship. All right. The domestic hot water, things like that. All right. Now, if we were to just take steam and put it right into the top of there, it wouldn't end well. All right. We would, a couple things could happen. We can get some, this would be wicked hot to the touch. All right. Don't want to touch it. That would be bad. The other thing that could happen is that we can get condensation inside of there. What if we shut down the ship to go into shipyard? Well, that 150-pound steam that's stuck up there is going to condense. It's going to turn back into regular old water, right? Because we shut down the system. It's not going to be at 150 pounds anymore. So all those reasons, things like that, is why we don't want that just swimming around in there. So again, 600-pound going in, 150 coming out. We sense it right here. All right. That sensing line goes up, and then it goes into the top of our control pilot valve. All right. A couple of different things could be happening here. We could have true steam going into it, or we could have just a little bit of regulation going on, and maybe this might be only 5 psi because of what our measuring device is doing. All right. Just for the sake of what you guys should know, is know that we are measuring down here. A signal is being inputted up into the top of our control valve. All right. So we have something being measured, and it's being sent to the top of our control. All right. Now we have an air supply going in. We have so many air compressors on the ship. All right. One of which is designated to control air. So if you're using needle guns or a pneumatic tool, those tools are not going to be drawing from our air supply for our control air. All right. So we're going to have a fully separate air compressor that goes to a fully separate air tank that will be going into our air supply. All right, so that no other person, nothing else going on the ship will affect this control system. All right, so this will come in at 120, 100 psi, somewhere around there. All right. Now, using that, this control pilot knows that it always has about 120 psi air supply going in. And then based on this input, all right, because that input is what's happening in the system. Based on that input, it uses some pretty simple math. It's just basically it's a ratio that someone who designed the system figured out. All right. And it will send the correct amount of air, operating air pressure, to bring this up or down. Just like the gasket material, up or down, considering what happens. All right. So it uses that air supply. This air supply is what gets sent over here, but only a certain amount. It might be 10 psi. It might be 100. It all depends on this input. Okay. Does this make sense? All right. Remember, once again, We measure here. This sends a signal to our input. All right. We have our control air going in. Based on a ratio, if we have 5 psi in our input, it means it's going to take 10 psi of our air supply and send it to our regulating valve. Or if we have 20 psi in our input, it takes 100 psi and send it to our regulating valve. All right. This is basically, like I said, it's a ratio. It's a conversion. All right. That's all what's happening in this piece of equipment. But it's in the physical world. Okay. Is anybody not getting this? Because this is quite literally everywhere on the ship. All right, good. So, like I said, other controls. And this is how we can get other controls. If it's measurable, we can measure it, we can turn it into a signal this way. All right. So temperature can be sent in as a signal, flow, level, anything. All of this is done, and why I'm not getting into it, that you can take any of these things are a very mechanical, even at the most digital level, is a mechanical version that we can create a signal with. All right. Now, we have something called normally closed valves. All right. So in everyday operation, if you just buy one of these valves and you just grab it off the shelf and hand it in your hand, this is my valve, and you put it in your hand, it's normally closed. If you put it in the system, it will be normally closed. The only time that that normally closed valve will open is under one condition. All right. And an example of that is a relief valve. Okay. So we have a relief valve right here. All right. Another symbol that you can use for a relief valve, it looks like that. All right. You notice it's coming out of our discharge of our pump and goes into the relief valve. You don't want that relief valve open normally. Only a certain condition would you want that to be open. All right. And if you notice, remember, we're using fuel oil here. So why is this going right back to the beginning part of this pump? Why would we want it to go back into the suction? Why not just go to atmosphere?
Because you don't want to be spraying fuel over your ship because then you have a hazardous condition.
Exactly. So if you come walking over and you're standing right here looking down at your pump because it's making a weird noise because God knows that you're going to be walking around that engine room and hearing some weird noise and right before the relief valve kicks off and you get a space full of fuel. All right. And same thing, you don't want an environmental condition. Really the only time where a relief valve will go to atmosphere is going to be something like an air tank. It will be something where it's not going to be harmful to the environment. So that will even be in potable water, stuff like that. Nothing where it will actually damage anything. All right. So fuel is going to come out, go into the relief valve. And unless there's a certain pressure, say you have this discharge valve closed, we're going to be building up pressure like crazy, right? And we don't want to bust anything. We don't want to break this pipe. Well, we'll just relief it and it'll go right back to the front. It'll suck it up and it'll push it right back out and it'll stay below whatever this is set at. All right. And then as soon as you open up this discharge valve, because you realize the mistake you made, well, you would want this valve to close because you would want it to be normally closed. So it goes back to its normally closed position if it goes below that one condition. All right. So again, here's some pictures. Here's a picture of a relief valve. Here's one of a safety valve. All right. So that way, remember the difference. That's a big difference between these two. Relief valves will open and close at the same pressure. A safety valve will open at a set pressure. and then close at a pressure below that. All right. Another one is something called a bypass valve. All right. These are important. They're pretty much around all pieces of equipment. All right. Now, if we sit here and we take a look, we have this meter right here. All right. Well, this meter might be a piece of plastic. It might have a plastic turbine inside of it. You know, one of those little kid things, a little pinwheel that turns a rotation, a really mechanical version of a meter. Well, what if that breaks? All right, and it clogs up. Well, would we want to shut down the entire ship? Imagine this isn't a school ship. This is, you know, steaming across the Atlantic. We have places to go. We have cargo to deliver. Do we want to shut down everything just because of a simple little meter? No, right? So that's why we have bypass valves. So that way we can close our isolation. All right. Coming back to those isolation valves again. So we close those isolation valves and we open up this bypass. We can now service this meter and we can keep the ship running. All right. That's what those bypass valves are for. They're normally closed, but for one condition, a broken meter, a clogged meter, the meter's leaking, you know, anything about this meter not functioning at full operation, we're going to open up that bypass. All right. So that's another normally closed valve. And then we have recirculating valves. They will normally be closed, but there's some conditions where they would be open. All right. Think about it. We have 4 burners, right, on each side of the boiler. We want a certain amount of pressure and a certain amount of flow going to all of those burners no matter what, right? Are we going to sit there and tell the computer or tell the automation that we need 2 burners, 3 burners, 4 burners? Are we going to be turning on and off this pump because we only have 1 burner and we don't want to get too much pressure? So we have recirculating valves that will allow flow of fuel to constantly flow through the system, and we'll be delivering the same amount of fuel to each one of these valves, to each one of these burners at the same pressure. Diesel engines do this. All right. Whether you are going at a fast, high RPM, revolutions per minute, or you're going at a slow revolutions per minute or RPM, you want the same amount of fuel delivery. So you would have a recirculating valve. All right. Ours is just a lot more manual. All right. So, any questions on that? Anything we want to go over again? Because remember, quiz Friday. All right. Last class and this class. Anything you want to go over?
Professor, just a quick question. How are we making up that quiz on Friday?
How are you?
I could do it at work real quick at a different time if that's fine. I mean,
Why don't you come to my office hours on Wednesday?
Wednesday? Okay, sounds good.
1:30 to 2:45.
All right.
All right. We'll do it then.
Thank you.
Yep. For the quiz, make sure if you have any sort of learning or you need extra time, Thursday evening is the latest I'll accept anything. All right. After that, it will be the day before the next quiz. All right. Same thing goes. It's just, I don't want to be adding names to, makes it more difficult on the admin side. All right. So just get it done. Going from there, I don't know if I said quiz is going to be like 10 questions long. It's going to be all in one go. So that way you don't have to worry about backtracking or anything like that. I'm not using the Respondus lockdown browser because you can't use Zoom at the same time. It starts exactly at 3. You'll have, I think, either 10 or 15 minutes. I haven't decided yet for 10 questions. All right. Anything that I've said, anything on the PowerPoints are fair game. That extra information is for you guys. I'm not going to be pulling stuff from there. Okay?
Is it all multiple choice or is it free response or a
All
mix?
multiple choice. Everything's going to be multiple choice. It gets you ready for the Coast Guard. And that's what these classes are all about.
Everything that's on the test can be found in the PowerPoint, right?
That or what I said in these lectures. All right.
These lectures are going to be posted on Blackboard, right?
So they are all posted onto YouTube. I linked.
Oh, YouTube. Sorry, I forgot.
Don't worry. So they're all there. Again, like I said, that's just for these classes. I do have my summer, when I taught this class during the summer during for 540. So pretty much every single lecture is up on that channel, so you can see all of them. All right. But they're all linked in there. So there's the 3 p.m., 10 a.m., and 11:30 a.m. lectures. All right. And again, there is no lab until the 25th when we start. All right. So the first day of school, you will have lab. All right. I'll get more into that on Wednesday because that's the last day of this. All right. Anything else? Any questions? Everybody understand the regulating valves?
Nah.
All right. There is no questions. We're going to go right into the next topic because we can gain time anywhere. Let's gain it. All right. So this is not on the quiz on Friday, okay? Only valves. So this is piping. All right. So piping refers to any assembly of pipes, tubes, valves, and fittings that form all or part of a system for the conveyance of fluid. All right. A pipe refers to a non-flexible fluid. All right. It's designed by diameter and wall thickness, strength, or schedule. They refer to the same thing. All right. Wall thickness. Then we have tubing. All right. Can be and usually is bent at installation. It's more flexible than pipe and is designed by nominal outside diameter and walls thickness. We have fittings. Those are devices employed to join sections of pipe, tubing, or hose in a piping system. Now, we have nominal pipe size, or NPS, is an approximate inside diameter of a standard pipe, Schedule 40. All right. Example. We have a 3-inch STD pipe. All right. The outer diameter is 3.5 inches. The inner diameter is 3.068. The wall thickness is going to be 3.5 minus 3. Divide that by 2. We will get the actual wall thickness there. All right. Now we have a 3-inch XS, or scheduled 80. All right. This has an outer diameter again of 3.5. It has an inner diameter of 2.90. All right. The wall thickness is now 0.3. Then keep getting smaller. And we got schedule 160. All right. So we can see as our numbers increase, we're getting a smaller inner diameter, but our wall thickness is increasing without increasing our outer diameter. All right. So if you were going to go and order one of these pipes, what would we want to need? What would we need to know?
Inside and outside diameters.
Well, we would want to know our inside and outside, but no one is going to, if you opened up Granger, right, open up your ordering paperwork, what are they going to be labeled by?
I'm guessing as like the schedule 40, 50, so on and so forth.
You're going to basically be seeing only that. All right, give me 1 second and I'll pull up an example. So I didn't expect us to get to this. All right, so found it. Pull this up. So I'm on Granger's website right now. All right. If we look, we have piping. So this is ABS piping. Doesn't matter. It's just piping. All right. We can go for pipe size nominal. All right. So this is 1.5 inch. It's 10 feet long. All right. ABS pipe. This one we could see it's schedule 40. So we'll know our inner diameter because of the fact that it's schedule 40. All right. We are going to know the outer diameter because it's 1.5 inch, and then we know our length. All right. Now, if we look, go back here, here's black pipe. It doesn't matter what it is every single time. Here's schedule 40 pipe nipples. That's a type of fitting we'll get into probably next class. All right. These are all the different nominal pipe sizes, overall length, but they're all, even though it's a 2 inch, 1/4 inch, 1 inch, 3/4, they are all schedule 40. All right. So that wall thickness doesn't change between any of these, but their nominal pipe size does. All right.
What does nominal pipe size stand for again?
So we have our nominal pipe size is that outer diameter. All right. So again, I'm not going to make you do the math to find out these wall thicknesses. It's just for your understanding. All right. Understand that schedule goes up, we have bigger wall thickness. All right. It's important to know that. All right. Because I worked dredges. That's where some of my experience came from. We had armor plated piping. All right. It started its life out at 3 inches thick. All right. Because every single day, 24 hours a day, 7 days a week, 365 days a year, this pipe all throughout the entire ship would be sandblasted all day long because we were sucking in sand. Our job was to move sand. So we would suck up sand in one location and then we'd blow it out somewhere else or we'd dump it somewhere else. That's what we were paid to do. By the end of 6 months, I was taking measurements on piping on the outside of wall. There's a device, an ultrasound device, that we can figure out how thick these pipes are. I had to do that because the piping that we just replaced started to crack and send slurry of sand and water into our engine room. This was basically what happened on a monthly basis. So we had to basically every 6 inches grind off some paint and then take a sounding. It was called a UT sounding. That 3 inch wall diameter, this 3 inches, was down to 1/4 inch in some spots. With other spots being so low that we couldn't even weld to it and plate on top of it. So understanding and knowing how to order and knowing what wall thickness is, what schedule it is very important. Because if you order the wrong material, when you get into shipyard and you need 3-inch armor plated piping and you order schedule 40 within, a nice little wall thickness of something that takes 6 months for it to get to, you're going to have a really pissed off chief engineer. All right. So these things are important to understand where it's all coming from. You're going to be the one on the ship ordering. You have the power to order whatever you want. In some companies, you quite literally can order anything that you say will get the job done and get it done faster. They will let you buy. We were getting ready to buy a battery-powered grease gun one time. We were trying to see how much we can push through ordering, but that's besides the point. Now, we have nominal pipe size, or NPS. All right, that's the other way you can see it. All right, for pipes with an outer diameter of greater than or equal to 14 inches, they are sized by the outside diameter. All right. So example, we have a 16-inch schedule 30. All right. So we have an outer diameter of 16 inches. We have an inner diameter of 15.25. That equals our wall thickness of 0.375. All right. We have a 16-inch extra small schedule 40. That gives us a 1/2-inch wall thickness, and so on and so forth. All right. So, tubing sizes. Outside diameter in inches or 16ths. So number 12 tube has an outside diameter of 3/4 of an inch. And number 16 has an outside diameter of 1 inch, and so on and so forth. Wall thickness is as a decimal, or in this wire gauge number. All right, so 16 BWG is equal to 0.065. An 18 BWG is a thinner wall, and a 14 BWG is a thicker wall. All right, it follows the same way as any sort of wire. All right, 12 gauge wire is going to be a thicker wire than if you had an 18 gauge wire is going to be a very thin wire. All right. So copper tubing is often designated by slightly different parameters. Its outside diameter as well as wall thickness. All right. So you have piping that is, you can have a 1-inch copper piping, again, by its outside diameter. You can have a 3/4, you can have 1/2 inch. All right. And then its wall thickness is not schedule, but in different letters or type. And this goes down to the type of material it's made, the composition of the copper, of how thick it is, all these different parameters. All right. So type K, L, or M. And K is the most robust. So it has the thickest wall, can stand the most pressures, things like that. All right. And not only that, but the thing you also want to concentrate on is where in the area is it going to be. All right. I just did a piece of piping in my garage that's exposed. All right. I had to reroute it. We had to use 1/2-inch piping. All right. And we had to get K for it because it didn't really matter. It's just hose water. But the issue is that it's routed on the outside wall of my garage where we hang a lot of things. So we didn't want it to dent and get destroyed easily. So we wanted a thicker, stronger wall. All right. It wouldn't come down to the fact that after 6 months, just like the armor plated steel of my dredging days would destroy this pipe. It came down to the area or environment that it's going to be in. All right. So things to think about. So there are different ways that pipes can be connected. Just want to see something. It's not what I wanted. That's what I wanted. There we go. So we can weld them. All right. So if they are 2 pieces of steel, very easy to weld. All right. we have what's called a butt weld. All right. So we're not a welding class, but these are things you should know. All right. This is what's called a V groove. It's grooved out on either sides of the pipe in a 45-degree angle. All right. On both sides. They connect up right onto each other. One is not inserted into the other. They are the same size, inner and outer diameter. This V groove is important. All right. Now, there are things out there called backing rings. They're disposable. You don't collect them after you're done with them. All right. It's a ring that goes on the inside of the pipe. It's supposed to keep the weld in that spot. All right. Now, as you weld it, you weld inside that groove. You are utilizing both pieces of metal. All right. And you will form a weld inside of there. All right. Again, it says the backing weld removed or grounded away. You're not going to be able to get that out on the inside. So
I was just about to ask, you just leave a backing ring on the inside of the pipe when you're done welding it up?
I've never used a backing ring.
Okay.
Most of the time, you pretty much are just going to weld these two things together. All right. Now, another type is, this is the one that has a slot in it. And more often than not, this is basically as far as when you use fittings. Pipe to pipe, that's what you'll see. If you're going to be like, this is a 90-degree fitting right here. A 90-degree fitting will have this type of piece. All right, where its inner diameters match up, as you can see. But this outer diameter right here is much larger, where this pipe will be able to be inserted into it. All right, and where the weld forms, let me clear it up so that way you guys can see this, will be around the edge right there. All right, and that's called a fillet weld. All right, most of the time you will not just weld once. You'll have a initial bead that will go there. So a bead of weld, all right? And then you'll have two more, all right? You'll put one more here. Oh, come on. If I draw too slowly, it does that. And then you'll put another one here. There we go. So you'll basically make it a much larger weld. Now, if you notice, there is a slight gap in there, correct? Was that just bad animation or is it purposely done?
Purposely done, I'm guessing to allow for expansion.
Mm-hmm. So we want to allow these to expand, all right? This may be a very cold piece of fluid going through here, or it may be hot. All right, but everything's going to expand at different rates. Even if it's the same material, it will expand at the same rate. But think about it. If it's going this way, this is going to heat up a lot quicker than this because you're getting a hotter fluid going that way. It's not all instant. All right, just because you have 90-degree water going through here doesn't mean that the steel over here or the steel over here for the first time is going to all be 90 degrees. All right. It will be a slow heating up all the way through. So you want that little bit of room for expansion. All right. Now, you can also do threading. All right. So threading, there's the American National Taper Pipe Thread, or NPT. All right. Now, this is not as the same as machine threads on nuts and bolts. All right. You cannot use a nut or a bolt and thread in a pipe onto it. All right. Those use not NTP, but they use threads per inch, or TPI. All right. So NPT is the National Taper Pipe Thread. So, or just call it National Pipe Thread. All right. If you notice, we have a slight taper. You can see that line right here where it forms. All right. This is an external thread. So it's external in reference to the pipe. And that is cut with a die. And that's what a die looks like right there. So the die uses, we're referencing the die now, the die uses internal threads to cut external threads on your pipe. If you want to use, oh, I didn't know that was going to be the next one. I thought it was taps. So if you're looking around the machine shop, that's what an NPT type die set is going to look like. They tend to be ratcheting. All right. Now, if you want to cut inside diameter or internal threads are cut with a tap, and that is a tap. All right. Taps use external threads to cut internal diameter threads. All right. We could see we have a little bit of space in between each one of those threads. All right. Same thing in here. We have those little ovals in there. All right. And that's allowed because think about it. We are cutting, we are removing material, correct? So every time that we do that, we want that material to go somewhere. That's why drills have those flutes that they go by, right? That's not just a waste of space. That's where all that wood material goes out and flows out. All right, it's the same thing here. All right, that is a good spot to end for the day. I don't want to push into too much of what we got to do on Wednesday. All right. Does anybody have any last minute questions? Everybody good? All right. Remember, sign your STCW, sign that lab agreement. All right. Quiz on Friday. After that, we have one more class online. That will be Wednesday. All right. Enjoy your weekends. Be safe. All right. Take care
But
of
we don't have the
yourself.
lab this week, right?
Nope. No lab until we reconvene on the 25th.
And we have the quiz this Friday, right?
Quiz is Friday. Only on valves. Nothing to do with piping. It's going to be found in the Blackboard on quizzes folder.
And we still go to Zoom, correct?
Yep. Zoom with your camera open.
Is there any update on your classroom change yet for when we actually go back?
No, I'm going to be basically keep watching that. I haven't looked at it in a couple of days. Check right now. It's loading. There we go. We get a glance. All right. So they're saying for us, we're going to be in the Mac 212, which is way better than Mac 100, which we were going to be in. All right.
Sounds good. Sounds good.
Everybody good? No more questions? Or if you do, stick around. I'll answer them.
Thank you,
See
Professor.
you guys on Friday.
Have a good one.
Have a good one.
Have a good one, Professor.
Thank you.
Thank you.
Have a good weekend.
See you on Friday.
Hi.
How you doing?
I'm in JStart, so I don't know if I'll get my boiler suit by the first lab. Will that be a problem?
So what I would do, if you're in JStart, what are they telling you? What's that lead 102 class telling you?
I can order my uniform on starting the 25th, but with the
Starting
boiler.
25th. Okay. Do you have work clothes?
Like Like, what do
Do
you
you have
mean?
stuff that you don't mind getting oily or dirty or anything like that? Because if you brush up against stuff, you just don't want to.
Yeah.
I don't
Yeah.
want you getting anything dirty and being disappointed.
Excuse me, Professor. They told us to wear jeans and like a t-shirt if we didn't have a boiler suit
Okay.
when we were doing in doc. So
All right. So yeah, basically just wear something that you don't mind getting dirty. You know, they might give you some more information. Ask your lead 102 instructor about that because this is something that you have to do. Don't go out and buy an extra boiler suit, but steel-toed boots. I don't know if the ones supplied by the school are still as bad as when I was there. I bought my own outside of the school. If you don't have steel-toed boots, get some hikers, something like that, but have some sort of composite or steel-toed boot. Okay.
Okay.
And that's just for safety reasons. Bring safety glasses and some sort of hearing protection.
Okay.
So like earplugs. I'll go all over this on Wednesday, so that way everyone's ready for come Monday. All right.
All right. I only have like rubber toed boots.
Okay. Brian, are you in the regiment?
oh yeah,
How is the boots?
boots, they're pretty good. I like them.
They're good. What brand are they?
Actually,
Because that'll determine if what I'm going to tell you.
All right.
I don't have them with me. Do you want to wait like a minute? Or-
That's fine. Don't worry about it. If you're saying that they're good, I'll believe you on that. They must have changed it. When I was a student, they were so bad they used to cut your feet when you'd walk in them. So we had to get new shoes. Yeah, just wear regular old boots, something that will protect your feet. No open-toed shoes, sandals, obviously, all that kind of stuff. Okay?
Okay. Thank you.
Yep, no problem.
See you Friday.
See you Friday. What do you got for me, Ryan?
I was just curious. How should I